Okay, so it's time to go ahead and begin today. So the big topic of the day, although there's some small topics within this big topic, but the big topic is structural modeling. And lab 2 is the first lab where we use structural modeling. But all the other labs this quarter, and also your final projects, they're going to be structural models too. And then when you take CPE133 and you build that microprocessor, that's a structural design. Okay, so this is the first structural design you'll be doing, but from here on out, you'll be doing the same sort of thing. So it's a pretty important topic. But before we get into structural modeling, I just want to review what we did last class. Okay, because the half adder and the full adder, they're going to be part of the structural model. It makes up the device called the ripple carry adder that you're going to build for lab 2. That's the part 2 of lab 2 is essentially putting these adders together to get what's called a ripple carry adder. So remember, we have the black box diagram, right? The black box diagram, it shows us the main inputs and main outputs. So how many inputs does the half adder have? 2. Okay, so I'm just going to call mine here A and B, but hopefully you're more descriptive. Remember, I've mentioned how it's a good habit to get into that instead of just calling your inputs B and B, maybe you have like AJ underscore A or something like that. Okay, so be more descriptive with your inputs and outputs than I'm being here in class. Okay, how many outputs does the half adder? Okay, also 2. And for these outputs, it's sort of important to call them what they're typically called, and that's sum and carry out. Okay, or just S and C. Actually, you don't need to carry out for the half adder. You could just call it C because we only have the one carry for the half adder. Okay, and then remember the truth table, right? Inputs go on the left side, outputs go on the right side. So since there's only 2 inputs, we only have 4 rows in our truth table. And then what did we find out about the relationship between output C and the inputs? Like what kind of gate was it? An AND gate, right? Because remember, we went over this last time, that for the carry output, you only get a 1 at the carry output when both inputs are 1, right? So that's an AND gate function. Okay, how about the sum or the S output? What kind of logic function was that? Right, exclusive OR. So remember, exclusive OR, you only get a 1 out when the inputs are different, right? You get a 0 out when the inputs are the same. Okay, so again, that's just a review of what we did last time for the half adder. So any questions about the half adder? Okay, how about the full adder? How many inputs? 3. Right, and here typically, one of these inputs you're going to call CI to carry in. And then how many outputs to the full adder? 2. And this is where you'll typically call the carry out, but carry out, just to distinguish it from the carry in. Okay, so like I said before, you don't really have to call this carry out, right? Because you don't have a carry in. Some people do, but you just leave it carry if you want to. Okay, and then since there's 3 inputs to the full adder and 2 outputs, okay, but since there's 3 inputs, how many possible combinations do we have? 8, right? 3 to the 3, which is 8. 0, 0, 0, 0, 0, 1, 0, 1, 0. Again, I'm counting in binary as I do this. If I use a mistake, correct me. 2, 4, 6, 8, right? 0, 1, 2, 3, 4, 5, 6, 7. Okay. And then how did we get the outputs for the full adder? equals 2. If what equals 2. If like, what are we doing here to the inputs to come up with these outputs? Yeah, we're just adding the bits, right? So, yeah, wherever there's 2 1s, it would be a result of 2. So, you know, like in this row, since there's 2 1s, when we add them up, you'd have a 1 0, right? Because 1 0 is 2 in binary. And then anywhere else we have 2 1s. Right, and then we add 3 zeros, of course, the result is 0. Any row where just 1 bit is a 1, the result is 1. Okay, so 0, 1, 0, 1, 1, and then of course this would be 3 in binary. So 1. Okay, and then you had to make 2 Carnot maps, right? 1 Carnot map for the carry out, 1 Carnot map for the S output, right? And then one of those Carnot maps, I think it was the one for S, right? That was where you probably saw that there was 4 single groupings that were diagonal from each other. So you could represent that output with exclusive or exclusive. Yeah, so any questions up to this point? So, you know, this was just all, you know, review from last time, right? Now I'm just curious, again, this wasn't required, but how many people were able to get both the half adder and full adder to simulate correctly last time? Oh, great. Okay, a lot of people, great. Okay, that's really good, because if you have both of those working, you'll see that you'll just have to add one more file, then get it to work with what we call a ripple carry adder. Okay. So now we're going, oh, actually, one more thing from last time real quick. And that was this example of adding 2 4-bit binary numbers. Remember that we said that when you do addition like this in base 2, it's the same approach as when you add in base 10, right? 2 multi-digit numbers in base 10. You just add column by column, starting with the least significant bit. Right, so we just start here, 0 plus 1, 1, there's no carry, 1 plus 1, 0, with the carry, and 1 plus 1 plus 1, 1 with the carry, and then 1 plus 0 plus 0, it's 1. So like we said before, you know, here we were adding 6 to 7, and you always check to make sure that your binary matches what you would get in base 10, right? That would be 13 in base 10. Well, just like how we would add these binary numbers, you know, bit by bit, that's how the hardware does it. Okay, that the hardware that you're going to build, which is called a ripple carry adder, it adds column by column, okay, bit by bit. So what you're going to see is you're going to need an adder for this column. You're going to need an adder for this column. You're going to need an adder for this column. You're going to need an adder for this column. So in order to add 2 4-bit binary numbers, the hardware requires 4 adding circuits. And you're going to see that we're going to use a half adder for this column, and we're going to use full adders for the other 3 columns. And why do you suppose we could use a half adder for this column? Because you can't use a half adder for any other column except for this least significant column. Why is that? There's nothing to get carried over. Right, exactly. This column would never have a carry in. Right? So that's why this column here can be a half adder. But all these other columns would have to be full adders, because all these other columns could have a carry from the column to the right of it. Okay. So you're going to see that our ripple carry adder, which is the hardware that can add these multiple bit binary numbers, well, for 4 bits, we're going to need 1 half adder and 3 full adders. Okay. You know, if you were going to add 2 64-bit binary numbers together, you would need 1 half adder and 63 full adders. Okay, so it's only the least significant bit column that you can use a half adder on. Okay. All right, so that's going to lead us into structural model. Okay, to make this ripple carry adder. That's the example we're using. But like I said at the very beginning of class, all the labs from here on out in this class are going to be structural models. And when you build a microprocessor in CPE133, that's also a structural model. So that brings us now to a black box diagram for this device called a ripple carry adder that we abbreviate RCA. Okay. And you see, the reason why I'm calling this a high level black box diagram is because this is going to show the inputs and outputs to our overall device called the ripple carry adder. Okay, the half adder and the full adder black box diagrams that you did last time, they're going to be part of our structural diagram, and they're called lower level black box diagrams. Okay. So the higher level black box diagram, this RCA, that's the hardware that's going to take these two 4-bit binary numbers. Okay, I'm going to call one A and the other B. And it's going to give us a result. And these 4 bits of our result, we're going to call the sum, or just S if you want. And then if we get a carry out from this addition of this column here, that would be this bit right here. Okay, now for this addition, this came out to a 0, right? Because there was no carry from that column. But this would be our carry out of our RCA. And in fact, when would the carry out of this addition be a 1? Like, what would A and B?
There's like 1.
Right. Okay. Yeah, we have 2 1s in this column. This would be 0, and we get a carry. And when would that happen? For what? Like, what example of A and B, for example? Like, what would I have to add A and B together to get?
Just that first digit.
Say that again.
The first digit.
Okay, and can you give an example when that was happening? Yeah, 10 plus 10. What else? In fact, for every result equaling what would you get a 1 for that carry out? 16 or greater, right? If you get a result of this addition that's 16 or greater, this bit would be a 1, correct? Right?
Bigger. This is bigger than 32. There'd be some interest for you.
Yeah, then you're like running out of bits kind of thing. Yeah, so yeah, you're right. There is a limit on the top end. So yeah, it'd be 16 to whatever the limit for that number of bits. But the key point I wanted to make is that as long as this addition is 15 or less, right, you won't get the carry out. But once you hit 16 or more up to the limit you're talking about, then the carry out is going to be 1, right? Because this bit here of the result, this is like this, the bit that counts 16, right? Because this is the 1s, the 2s, the 4s, the 8s. This is the 16s here.
How can it pass multiple different bits with one output?
Well, here, this S output, just like this A input and this B input, are 4 bits. But you could have another, another ripple carry adder where there's more bits, like you're adding more bits, and therefore the sum would be more bits too. But for this example here, we're adding 2 4-bit binary numbers. So our sum is going to be 4 bits. And then just if there's that extra bit, we call it a carry out. Okay. So the reason I talk about this is because now you should be able to tell me for this RCA, how many inputs are we going to have? What are our inputs here? A and B. It's what we're adding, right? So A and B. And then you may not remember this, but I mentioned this probably like a week ago, just kind of like in passing. But when we have an input or an output that's more than 1 bit, do you remember how we signify that on the diagram? Yeah, you put a slash and then you put the number of bits. So you see this is going to be /4, /4. See, that tells us that this A input is 4 bits and this B input is 4 bits. Right, everything we did prior, like, right, your inputs and outputs for the half adder and full adder, right, they didn't have slashes because these are all single bit inputs and outputs, right? But when you have an input or output that has multiple bits, you signify it with a slash along with the number telling us how many bits there are. How about how many outputs do we have? It's going to be 2 because we're going to have sum as the output and then also carry out's going to be the output. Okay, so sum is 4 bits. Carry out is just a single bit, so you don't put a slash. Okay. So again, where these black box diagrams come in handy when you're doing your code in Verilog is you just got to look at your black box diagram to see how many inputs and how many outputs you have, and also to see whether you have multiple bit inputs or outputs. I don't know if you noticed, but in Vivado, when you declare your inputs and outputs, you know that menu comes up and you name it, right? You name your input or output, you choose whether it's an input or output. And then if it's a single bit, that's all you need to do. But if it's multiple bits, there's a little checkbox. Okay, so on Vivado, like a little checkbox, and next to it is the word bus. Bus is a word that's used that means a multiple bit input or output. So for A, B, and S, when you're at that part of Vivado, you're going to check them. You're going to choose it. And then another little menu comes up with a pull down. And you're going to choose 3 for the MSB. And you're going to choose 0 for the LSB. So what you're telling Vivado is that that input is a bus that's 4 bits. And by convention, we call the least significant bit the 0th bit, right? Because this is the 2 to the 0 column, right? So that's why we call it the 0th bit, right? And this is your 1 bit, right? And this is your 2 bit, and this is your 3 bit. Right? So you see your most significant here, because it's 4 bits, your most significant would be the 3rd bit. You mean in Vivado? Yeah. It just because it gives you a place to put it. Yeah, it doesn't, I guess it doesn't assume that, you know, it's 0. And I mean, you could, Vivado will let you number the least significant bit whatever you want. Like you in Vivado, you could call this like the 3rd bit and it's like the 7th bit. I mean, it's still 4 bits, but that would just not be conventional. Yeah, I mean, your question's a good one because you would think they would just default to 0, but as far as I know, it doesn't. Yeah, so I have to tell it.
What is the variable input in there, or is it variable?
Well, no, oh, you're saying the carry into the RCA. Yeah, the RCA doesn't have a carry in. No, I mean, our RCA doesn't have a carry in. Now you could have an RCA that has a carry in, but yeah, ours doesn't. Yeah, you bring up something that actually comes up a little later on in the course, but yeah, right now we just got these 2 4-bit inputs A and B that we're adding. Okay. Okay, so now, like I said, that's the high level black box diagram. It gives us our main inputs and outputs to this RCA, this ripple carry adder that's going to do this 4-bit binary addition. So now let's actually talk about what a structural diagram is, which is also called a low level diagram. So notice I got this dash box, okay, around these 4 squares that we're going to fill in real soon here. This inside this dash box represents what's inside this high level black box diagram. So up here, see, this is going to be our A input. It's going to be our B input. So you see here are our main inputs coming into the RCA, and now the structural diagram shows of what's the RCA is made out of. Okay, and likewise down here, you know, this is our S output, and you know, this is our carry out. Okay. All right. Well, the reason I got 4 boxes here is because each box is an adder. See, this adder is going to add the least significant bit column. So this is going to be the half adder. But actually, let me write it in the middle. I'm going to write something else up top here. Okay. So this is going to be a half adder, right? Because that's going to add the least significant bits. These other 3 are full adders. Okay, because as we talked about, these columns of bits would have to have a full adder because you could get a carry in from the previous column. Okay, so this half adder is going to have the inputs that you named. Right, again, you were probably more descriptive than what I'm being, at least I hope so. Okay, so this is going to be the AB, the half adder. This is going to be the S output. This is our carry. Okay, and then same sort of thing here. Right, A, B, this is CI. S, this is 0, right? Whatever you call the full adder inputs and outputs. Okay, so I just filled out each box here with what I had for my black box diagrams for my half adder and full adder. Okay. Now, coming into this half adder, okay, the bits that this half adder is going to add are the least significant bits of A and B, the 0th bit of A and B. Okay, so you see coming into here is going to be just the 0th bit of these 4 bits. And the way that we identify like a particular bit of a bus is we put that particular bit number in brackets. Okay, so you see we're just taking the 0th bit of A, so we would show that as A bracket 0. And same thing with B, B bracket 0. Right, and then this full adder is going to be adding the number 1 bits of A and B. Right, so you see this would be A bracket 1, this would be B bracket 1. Okay, and then this full adder is going to be adding the number 2 bit. So this is A bracket 2, this is B bracket 2. Okay, and then we have A, the 3rd bit here, the most significant bit, being added by this full adder. Okay, and this half adder is going to give us the 0th bit of the result, S. And then notice we take the carry of this half adder and connect it to the carry in of the full adder right next to it, right? Because that's what you would do manually, right? Okay. And then this would be S1. Right, and again, see the carry out of that full adder goes to the carry in of the next full adder. This would be S2. Carry out of this full adder goes to the carry in of this full adder. This would be S3. And then this is the carry out of our result. That would just connect directly to this. See, this would just go right to there. Okay, so you know, these 4 bits of A come in and then they split up, right? Just the 0th bit here goes here, just the 1st bit goes here, 2nd bit goes here, 3rd bit goes here, same thing for B. Then for our results, we get the individual bits from the adders, but then we put them together to get the main output, the sum 4 bit. And then again, since the carry out is just a single bit, well, that's just like a direct connection, right, to our main carry out. Okay, so does everybody see what's going on here, right? That, you know, these adders, they just add single bits, right? But we're putting multiple bits into it. So those multiple bits actually kind of split up and go to the appropriate adder and then come back together again for the sum. Okay? All right, there's another thing here And that's in Vivado or System Verilog, when you make a connection between lower level modules. Okay, so each block here, each box, we call it a lower level module. Well, when you make a connection between lower level modules, you can't do it directly. You have to go through what's called an internal signal. So the next thing I'm going to write here is I'm going to write a variable for each one of these connections that are connecting the lower level modules. And again, I'm just going to write them very generally, but hopefully you're more descriptive than what I'm being. See, I'm just going to call this connection between the carry of this half adder and the carry in of this full adder. I'm just going to label it T1. Okay, and that's going to be something called an internal signal. I'm calling it T1, but maybe a better description when you do it, maybe a better description would be like bit 0_carry or something like that, And then likewise, this connection here, I'm going to label T2. And this connection here, T3. See, you only have to define these internal signals between lower level modules. You don't have to define them when you're connecting a lower level input or output to a higher level. For example, when these bits of input A get connected to the appropriate adder inputs, you don't need an internal signal there. And same thing here, when these bits of S come together for this main output F, you don't need internal signals there. It's just when you connect lower level to lower level that you need this thing called an internal signal. And it's just the way how Verilog works. Okay? All right, so I should turn the camera. See, I remembered to turn the camera again. I'm getting better this quarter. This will turn. There we go. All right, are there any questions up to this point? Just how, I labeled this and what this represents. Does everybody see that what's inside this dash box is what this RCA is made out of, right? This RCA, high level black box diagram, it gives us these main inputs and these main outputs, and now we're showing, what's inside here. So, what's inside here are these two that we've already designed, right? See, the structural model is what connects it together. Okay? All right, so let's go ahead and talk about now, what it's going to look like on Vivado and, what the code is going to look like to make this structural model happen. Okay, so first thing, we already talked about last time that in your source window for this lab 2, you're going to have a design file for the half adder, a design file for the full adder, and likewise, you're going to have sim files for both, right? Well, today, you're going to add another file that's going to be the structural model, and maybe you call it RCA. That's right for System Verilog. Okay, and you're also going to need a sim file for that RCA. So, provided that you have already simulated the half adder and full adder successfully, once you build your RCA, and I'm going to show you the code or give you some of it anyway, you'll have to simulate the RCA. So when you simulate the RCA, you're going to have to make it the top module. So remember how we talked about the pyramid symbol tells you what module is the top module? Okay, so just like when you sim the half adder, these two had to be the top module, right? When you sim the full adder, these have to be both top modules. Or when you sim the RCA, your RCA design source and your RCA sim have to be the top module. Okay. Now, before I show you the code that will actually make these connections, I just want you to recall the simulation file. And I talked about this a little bit in my intro to Vivado video, but you might have missed it. But in that video, I talked about that this line in the sim file, right? You know how this is the design source name that you want to test, and then UUT stands for unit under test. But this part right here is what I want to focus on. Okay, this part of that line that's in your sim file is doing what we need to do in the structural model to make the connections we want to make. Because as I talked about in that intro to Vivado video, this code right here, okay, this dot FLC underscore A, which is what I call my input to that first logic circuit. And then in parentheses, this TV underscore A, and TV underscore A is what I call the A input of my sim file. Well, this code right here is making the connection from that input of my design source to this input of my sim file. This makes a connection. Okay, and same thing here. This was making the connection from my design source FLC input B to my sim file input B. All right, so this dot name in parentheses name, that's what makes a connection in Verilog. Okay, so you're going to see we're going to be using the same syntax to make these connections in the structural model. Okay, all right, so let's go ahead now and let's see what the code, the Verilog code, is going to look like for your RCA. So just like any design source, you always start off with the module name. Now, I may make mistakes up here in the syntax, so I'm just giving you kind of an overview of what you have to do. Understand that you got to be more careful than what I'm being. I might make some syntax error. I'm not really, not being conscious of that. But you got to name the module. So maybe you name it RCA. And then I think there's parentheses, right? And then you've got to put your inputs and outputs, right? That's where you declare your inputs and outputs. So this is where you declare your main inputs and your main outputs. You can fill out the menu that we talked about, right? That, has the bus to check off, or some people just type it right in. When you get to that part where it asks you with the window to put in the names of the inputs and outputs, you could, if you wanted to, like some people do this, they skip that part and then they just manually type in their inputs and outputs. Okay, or sometimes people will take like a previous file that's similar to what they're going to do, for a new file, and they'll just do a copy paste and edit. So, if you don't want to go through that menu portion of Vivado, you don't have to. But here's something that you haven't seen before, and that's what a multiple bit input or output looks like when it's declared. Well, it looks like this, like say the A input. In Verilog, the way you declare a multiple bit input or output is you put brackets, and then you put the most significant, the least significant number. So again, since these inputs and outputs are 4 bits, you'll have 3 for the most significant, 0 for the least significant, and then you just put the name of the input. And, well, you got to call it input too. In Verilog, does input go after the name or before? I can't remember. It goes before. Okay, so it's over here. Thank you. All right, so the only difference from what you've done before when you have a multiple input or output is you have to put in brackets, the most significant number, the least significant number, to tell, it tells Vivado that, it's not 1 bit, it's a multiple bit of, and it's 4 since it's 3 to 0. Right. So you'd have to do that for the B also, you'd have to do that for the sum, and then the carry out is just going to be a single bit. So that's just like you had before. Okay. All right, so so you'll have to put your inputs and outputs there just for the RCA, right? Because we're doing the RCA now, so it's going to be A and B inputs and S and C outputs. Okay, and then you'll have, once you declared your inputs and outputs, it's like parentheses and then like a semicolon, I think, right? And then in previous designs, you would then write your code after this. Okay. Well, when you're doing a structural design, the next thing that happens, or the next thing that you type in after you declare your inputs and outputs, is you declare these internal signals. Okay, and the way that you declare internal signals is you use the word logic. And these internal signals are just single bit, right? Because you're connecting this carry to this carry in, and they're both single bits. Okay, so if it's single bit after logic, you just put whatever you're going to name it. So, you know, you put like T1, and then since we have multiple, you just separate them by commas, T2, T3, and then semicolon. So in system Verilog or Verilog, to put a comment is a double slash, right? So you see, this is how you declare internal signals. Now, not in this design, but in some future designs and also in an activity that you're going to work on. Just like you can have inputs and outputs that are multi-bits, you can have internal signals that are multi-bit. Okay, here they're not. Here they're just single bit. But if you had internal signals that were multi-bit, you would do the same thing as you did here. You just put in brackets, you know, whatever the most significant bit number is, least significant bit number is. Okay, and that tells Vivato, you know, that that's multiple bits. Okay. All right, so now our internal signals are declared. Now comes the code that's going to make the connections. Okay, so what you would write next is first, I'm going to put HA. Okay, this is the file name of what we're connecting. So I'm going to start with connecting the half atom. All right, so I don't know, you might want to write in your notes somewhere that you always start with the file name. You know, so whatever you call this, you know, if you called this something else, that's what you got to put here. It's got to match the name of your half adder file. Okay. Then the next thing that comes after the file name is a label, and the label can be anything. You know, I'll put HA_0. Okay, this is a label. And again, label can be anything. Okay, but this has to be the file name. If it's not the file name, it's not going to know what you want to connect. Okay, and now after the file name and the label, now comes this syntax right here, where we're going to make the connection. So it's parentheses, and then I look at my half adder and I go, okay, I want to connect input A of the half adder to the 0th bit of my main input. So what that would look like syntax-wise is I put dot A. Okay, so you start with whatever you want to connect from the half adder. And then in parentheses, I would put A bracket 0. So this syntax is going to connect A of my half adder to the 0th bit of my A main input. And it is okay to have them name the same thing. Okay, the software is smart enough to know. And the reason it knows is because whatever you put after this dot means A of the half adder. And whatever you put in the parentheses is what it's connecting it to. Okay? So it's the same idea for the rest here. That to make this connection from input B of the half adder to the 0th bit, I would put dot B, and it's separated by commas. This is a comma. Okay, and then I would put B bracket 0. Right, so that's going to make the connection between this B input and the 0th bit of my main input. Okay, I would also have to have dot S, and then in parentheses S0. Oops, that's a bracket, not a parentheses. It's got to be a bracket for what you put this number in. Okay, so that makes the connection from the S input of the half adder to the S output 0th bit. Okay, so here's where it becomes a little bit different. To connect this carry out of the half adder to this carry in of the full adder, I can't do it directly. In other words, I can't do dot C in parentheses CI. Okay, Verilog doesn't allow that to happen. The way I do it is I first make a connection between this carry out of the half adder and this internal signal. Okay, so you see, this is going to be dot C, and then in parentheses T1. And that's the last thing I got to connect to the half adder, so I would end it with parentheses, and I think also you got to put a semicolon here. Okay, so this syntax here is going to make the connection between this carry output of the half adder and this internal signal. So at this point, the carry of the half adder is not connected to the carry in yet. You'll see it takes one more piece of code to complete that connection. Okay, but this would be the line for the half adder. Okay, so this would take care of the connections for the half adder. Okay, so before I move on to the full adder, do you have any questions about what I wrote here? Does everybody see? Do you see how it's the same syntax as that part of the sim file, right? Okay, all right, so now we're going to connect up a full adder. So I'm going to do this full adder next. So I put the name of the file, the full adder, right? So I called it FA, so I put the file name. Okay, now goes a label. The label can be anything. I'm going to call it FA_1. Okay, and then I start another line. So, it's the same idea as before, right? Dot A, in parentheses, I put A1, right? Because I'm connecting the A input of the full adder to the number 1 bit of the A input. Okay. Now, do you want me to write B in, well, I will. I'll do it. But just easier just to do it. So B, or I should ask you, what am I going to put in parentheses here for B, to connect B of this full adder? B1. Yeah, just B1. Okay, and then we'll do S, so dot S, and then what do I put in parentheses? S1, right? All right, but here's a main point I want to do. Now, with CI, I connect CI to T1. So since I connected the carry of this half adder to T1 in the previous line, now when I make this connection from CI, the full adder, to T1, that's what makes the connection between the carry out of the half adder and the carry to the full adder. Like those two together make the connection. Okay, so this would be dot CI T1. So you see those two together make that connection from the carry out of the half adder to the carry of the full adder. And then I would also need to do dot C0 to T2, right? So that would make this carry out to this internal signal. And then the next line would finish the connection when I connect CI to T2. So T2 would go here. And let's see, have to close the parentheses and then a semicolon.
So what does our carrying come after our house? If carrying is an input and that's not.
Oh, you mean the order?
Yeah.
The order doesn't matter. Like I could put this first. Yeah, order of the connections doesn't matter. Now, when you make a connection like this is always an input or output of that, that box that you're connecting. So, I always start with an input or output of what this is here. But then here goes, whatever I'm connecting to. But like the order of these connections, like the S could be here, the D could be here. It doesn't matter the order of the connections. Okay. Now, another key thing, because people often miss this. See, when I do the next line, it's still going to be the same file. See, there's 3 full adders in this structural model, but I'm just using the same file 3 times. it's not like I need, this is the mistake people make. Is people will think they need 3 design sources, like 3 separate full adder design sources. No, you don't. You only have a single design source for the full adder, but you're using it multiple times. So this third line to connect this full adder, it's just going to be FA, and then you give it a different label, like FA2 maybe, and then you just go ahead and write the connections. But you only have a single full adder design source. It's just the structural model is using it multiple times. Okay, so you'll need a line for the full adder FA2, and you'll need another line, right, for your third full adder, and then you're finished. Okay, so that's all that goes in your structural model. You got to declare your inputs and outputs like you do in any module. You're going to have internal signals. That's new, right? You don't see internal signals in the other design sources, or you haven't yet anyway. And then you've got the block of code, these 4 lines that's going to make the connections. Okay. All right. So I'm going to let you fill out the rest. Okay. But do you have any questions up to this point?
What does the C0 for the last one mean to?
Oh, yeah, that's a great question. Yeah, it's just going to be dot C0, right? And then in parentheses C0. Because see, this is connecting a lower level output to a higher level output, and you don't need an internal signal for that. You only need internal signals when you're connecting lower level inputs and outputs together. So yeah, in your 4th line, like right here, you're just going to have dot C0 in parentheses C0. And again, the software is smart enough to know that even though these are called the same thing, because you started or you put a dot in front of this one, it knows the start there, and then it's just going to connect to whatever other C0 there is, which is only one. So yeah, so it's not like sometimes people think you have to name these different, but the software is smart enough that it will know.
Basically a separate output from us. That's just kind of like.
Correct. Right. And you see that's shown in the high level too. Yeah. Yeah, you're going to see, there's an earlier question about, why isn't there a CN? And it just so happens at this point, you don't need a CN, but you're going to see in a couple of weeks. We're going to come back to this and we're going to put a CN for this, and you'll also see that, you could have a ripple carry adder, although I don't think they're very popular like this, but I mean, it's not inconceivable where you could have a ripple carry adder when you don't have a carry out output. Like maybe you just care about the sum, but we have a carry out because I think it's next week. You'll see we're going to use that carry out to do something. Yeah. So like most things that, what you're interested in just depends on what your objective is, All right, so any other questions up to this point? Now, you have enough now where you can, do this third file that you need for lab 2 to get this RCA to work. But there's still a few more things I want to go over before you start on your work. One is I just want to point out a few things on the activity for today's class. And then after that, I want to talk about these test cases for the RCA. So let me put this screen down and show you the activity. Okay, so this is the activity. So you're given 3 pieces of code. These are all separate. See, there's a module sort, a module pizza, and a module fruit. And they're each structural models. So you can see here, the inputs and outputs are first declared, like we were talking about after the module name. Then you have your internal signals. This is what I mentioned where an internal signal can also be multiple bits. So you see like here in this code, T1, T2, T3, T4, those internal signals, they're 2 bits, right? 1 to 0, so 2 bits. And like down here, you have some internal signals that are 3 bits, 2 to 0. And then what follows is the code for the connections. So, you give them file names and labels and then what the connections are. So what the activity is to take, each one of these. And here, for the majority of the activities, I've been saying, make sure every student does, the entire activity and then choose one to pass in, mix them up, however you want to choose them in. Here, if you do one of these and you're comfortable, I would say that's okay. So if you wanted to split it up, like one person does this, one person does that, one person does that, that's fine. As long as after you do one, you understand what's going on. If you do one and you feel like you need more practice, then definitely do more than one, okay? But there are a couple of things I wanted to point out real quick. One of them is, let's see. And what I'm about to point out here has to do with the handout that we have. There's a handout on each table. Okay, this handout here. And this handout talks about splitting bits, something called concatenation and replication. Out of those 3 things, splitting bits is something in this class that you need to know about. And also concatenation is something you need to know about for this class. Replication is kind of a good thing to know for this class. You don't necessarily need it. But I put it on there because for the next class, CPE133, that becomes more important in that class. But I just wanted to point out some examples of splitting bits and also concatenation. So first, and I apologize if this is hard to see, but this is on Canvas. So if you have a computer, you'll probably be able to see it better. I know the resolution on the screen here is not the best. But an example of splitting the bits is that if you look at this example here, this internal signal, T1, it's 3 bits, see 2 to 0, right? So 3 bits for T1. But then in this line of code where a connection is being made between input B of this black box called, or this file called Apple, and in parentheses, you'll see T1 in brackets 1 to 0. So you see, that's an example of splitting the bits. That T1 is 3 bits, but in this particular case, we're connecting this B, and we don't care whether it's an input or output, it doesn't really matter. Same thing. But we're connecting this B of this Apple black box, to only 2 bits of T1. See, because it's T1 in brackets 1 to 0. Okay, so that's what's referred to as splitting the bits. That sometimes you'll have like either an input or output that's more bits than what you actually want to connect to. Like sometimes you only want to connect to 2 of the 3 bits or 3 of the 4 bits, whatever it may be. And that's how you can do it. It's called splitting the bits. Okay. All right. Another thing I want to point out here is an example of what's called concatenation. Okay. And if we look up here at this example, you see our internal signals here, T1, T2, T2, T3, and I think that's a 4. Yeah, 4. They're declared as 2 bits, right? 1 to 0, 2 bits. Well, then if you look at this line of code here, where we're making this connection, we're connecting something, H. Again, it could be an input or output, it doesn't really matter. But then in parentheses, and I'll write this out so it's clearer. Okay, so in parentheses, we're connecting this, thing called H, I think, was it H? Yeah, H. Right, so we're connecting whatever this H is to what's in the parentheses. And then in the parentheses, you got this brace, right, the squiggly bracket. And then you have a 1. And then you have a T2, and then a close of the squiggly brackets. Okay, well, when you have the braces, the squiggly brackets, that's when you're doing what's called concatenation. And concatenation is just joining bits together. So this T2, right, this internal signal T2 is 2 bits. And we're adding on to it a 1. So that's going to make this 3 bits, right? It's going to take whatever 2 bits, 1 colon 0 is, and it's going to add a 1 to the left of that. Okay, so you can use concatenation to take, take some, internal signal, or it could be an input or output of a certain number of bits, and you can add bits to it. And you can add bits to the left of it. You can add bits to the right of it. Like if I wanted to add it to the right, I would just switch the order. Also, you could add zeros instead of ones. Okay, but the key thing is when you concatenate, you're joining together. When you're splitting the bits, you're kind of taking it apart, as the name implies.
Do you want to do this for our 2 outputs here?
I mean, we don't want to do that in this particular case. I mean, that's something in a different design you may want to do for some reason, like take C0, put it with S and make it a 5-bit output. But for reasons that will become more apparent coming up, we don't want to do that. Because yeah, we're going to use this separate carry out for something, I believe it's next week. But for another design somewhere, that could be perfectly what you would want to do. And concatenation would be the way you want to do it. Like in brackets, you would just have like C0, C0, then comma S, and that would put them together. Yeah. Yeah. So there are circumstances where what you're suggesting you would want to do. It's just in this particular case, we don't want to do that. Okay, and then like I said, the third one on there is replication. For this class, we don't really run into that. CPE133, there's cases where that can be useful, but as the name implies, replication is you're just taking something and repeating it a number of times. So I put it there just for you to look at and have as a reference. Okay. All right. So any question now? So what the activity is taking this code and drawing the structural diagram. So, I went this way, right? I had the diagram and I showed you the code. The activity is going the other direction. And the answers are on Canvas. Like I said, if you do one of these and you feel good about it, you don't have to do all 3. But if you don't feel good about it after doing one, definitely do more than one. Okay, but the answers are here so you can compare, see if you get the same thing. So last thing, and then you can get started today. I want to point out, in case you haven't seen this, because we are on lab 2 now, the test cases for all the rest of the labs this quarter, except for the final project. I'll give you the final project test cases for the individual one when we get to it. For the team one, the test cases are going to depend on what project you do. But for the labs from here till lab 6, this file on Canvas shows you what the test cases are. So the test cases for lab 2 for your RCA. Now, okay, this is another confusion point, okay? But you got to keep things kind of like straight in your mind. There's sort of like a hierarchy here. These are the test cases for your half adder, right? Because this truth table defines the half adder. These are your test cases for the full adder. Your RCA has different test cases, right? Because your RCA, you're adding 2 4-bit binary numbers, okay? So if I wanted to test every possible combination of adding 2 4-bit binary numbers, can you guess how many, or can you estimate how many that would be? Yeah, it is. Actually, that's not an estimate. That's exact. 256. How did you get that?
6 squared.
Yeah, it's just 16 times 16, right? Because if you just think about it, like if you made this binary number 0 and change this from 0, 1, 2, 3 all the way to 15, right? That would be 16. Then make this a 1 and do the same thing, that'd be another 16. So yeah, 16 squared. So if you wanted to test every possible combination of adding two 4-bit binaries, that's 256 test cases. Do you want to write 256 test cases in your sim file? Most people don't, okay? I mean, you can if you want, but most people don't. So this is the first instance, and there's going to be many labs like this. And then when you take CP233, there's going to be many instances of that, and of what I'm about to talk about in that class, where to test every single possible combination just isn't, feasible time-wise. It would just take you a lot of time. So when you have a case like that, you have to kind of think about strategically, how can I test whatever I need to test in a way where I'm testing the design of it. Maybe I'm not testing every single possible combination, but at least I'm testing if the design is correct. Okay. Well, these 10 test cases that I have for the RCA have been strategically picked. Okay, so let's talk about how they were strategically picked. Do that. Let's go back to the whiteboard. So I took those 10 test cases that were shown in base 10, and I put them in 4-bit binary. Right, so these are the 10. See, 0 plus 0, then 0 plus 1, 1 plus 1, 1 plus 2, 2 plus 2, 2 plus 4, 4 plus 4, 4 plus 8, 8 plus 8, and then 15 plus 15. See, these 10 test cases, even though they don't test every possible combination, they don't test all 256 possibilities, they're strategically picked, okay, based on the design, right? Because we talked about how the hardware, when it adds these two 4-bit binary numbers, it's doing it column by column. We have an adder for each column. So can you see, if you just look at these two test cases, do you see what this is testing? What is this testing? The half adder. What are these two testing? Yeah, the first full adder. These two? Yeah, these two? Right, and then this is testing it all together with the two extreme possibilities. So, it's not a 100% guarantee. Okay, it's possible that your RCA could pass these 10 test cases and still, not pass all 256. I mean, it's possible, but it's unlikely, right? Because this is testing the design. Okay, so, I talk about this because, like I said, future labs in this class, and then especially in CP233. I mean, in this class, I give the test cases for the most part. I think actually, I think the final project individual, I don't give test cases for that. That I actually evaluate if you can come up with, strategically picking test cases for that final project individual, which is a 4-bit multiplier. Okay. CP233, most instructors that teach that class, including myself, we don't give the test cases that you need to test each little, block of the microprocessor that you end up putting all together. So it's something you need to kind of think about. Even though I'm giving you the test cases, you should always think about, oh, why are these the ones that are given? And you may even find like a better set of test cases. You might say, hey, Gary, this should probably be tested too. I've had that happen. In fact, that's how I gained a few test cases from good suggestions from students. So, okay, so you are now ready, or you should be ready to do the activity. And then after the activity, work on lab 2. You have enough now to finish lab 2. So do you have any questions before you get started? Okay, well, if questions come up, please ask. Kathy will be here in about 45 minutes to help out. All right.